Welcome to the Rocket Tech Podcast, Episode 2. I'm Konstantinos Durantis.
I'm Justin Fischetti.
And I'm Adam Kotler.
And this week we're going to be talking about ULA, Rocket Lab, Falcon Heavy, and maybe a few other things. So...
Only maybe, though.
Only maybe, though.
Only maybe.
Adam, why don't you tell us a little bit about what happened with Rocket Lab?
So yeah, last
Nothing.
night... Yeah, pretty much.
Started.
Last night at around 8:30 when the Rocket Lab window opened, Rocket Lab was supposed to launch, and they were at T-minus, do you guys remember?
T-5, I think.
T-minus, around, was it T-minus?
It was T-minus, I think, 19 minutes.
Okay.
Really?
Was that the first cut? Yeah, okay,
Yeah.
so then it was T-minus 19, and then a vessel appeared in there.
And it basically, it came pretty close. Probably not that close.
Launch radius, whatever.
It was like probably like just a fishing vessel.
So Rocket Lab, they launch from a site that is right near the ocean, as most rocket companies do, so that their boosters can fall back into the ocean and they don't hit anyone on land. And you can't launch if there are vessels within a certain radius.
Any, like, human or...
Yeah,
like,
if there's anything in the water, like boats or some dude kayaking or something, you can't launch because you don't want the booster to fall on them, so they have to wait until the person gets out of there. So,
what a shame, right?
Yeah,
Like,
so...
the safety protocols are such, like...
Dude, I don't know why we have them,
dude,
honestly.
it's not worth it.
So there was a vessel downrange, and they had to wait, and then that got the delay.
Yeah, and that wasn't the only delay. They restarted the countdown, and then I think it was T-minus 12. Yeah.
Yeah.
T-minus 12, Konstantinos and I went out to get some crispy chicken sandwiches, but then, by the time we came back, it was still at stuck at T-minus 12, and then they eventually closed the launch window due to weather concerns.
Yeah. Who would win, a bunch of engineers with $1 million rocket or a little boaty boy?
So the reason we try to focus on, or we brought up Rocket Lab, is because they're actually doing something very cool that hasn't been done before. Generally, when you have a rocket and you have the rocket engine, you need to supply it oxidizer and fuel, which are usually liquid. And
to have
generally,
combustion so that there's thrust.
yeah, pretty much. So
Like
you
how
have
in
that-
a car engine you have to give gas.
Yeah, and you also have to have a air intake, which is something a lot of people don't
What's
think
thrust again?
about. Thrust is pushy force for the rockets to go up.
Yeah, pushy force.
Pretty
Pushy
much.
force.
We're going to call it that.
So to create pushy force, you want basically a lot of fuel and a lot of oxidizer to go to the engines. To do that, you have these pumps. You can have turbo pumps. You can have a bunch of they're all these types of pumps. Generally, they're driven by burning that fuel. You have basically you have the rocket engine that burns the fuel and oxidizer and creates thrust, but it basically spins the pump and brings more fuel and oxidizer, so it basically speeds up the process.
It's the same way that a supercharger or a turbocharger works in a car engine.
Yeah, pretty much. And then the difference with Rocket Labs is that instead of using a pump that is driven with by burning fuel, they're using electrically driven pumps that are powered by batteries, which basically allows them to create a much smaller and less complex rocket.
It's not as cool as pressure-fed systems, though.
Well,
What we're doing, I'm not trying to brag or anything, but like, pressure-fed.
It actually is kind of cooler.
No, it's not.
I guess not. All right, so
What are they? What's their payload? Do you guys know?
It's well, for testing, I don't think it was
Some
anything
sort of
serious.
satellite, probably.
And this would be their first launch.
No, actually,
No.
They already did have a launch that was a failure.
Oh yeah,
What happened?
we tried setting up a launch party in
Oh
the
no,
lab,
no,
right?
even before that,
Yeah, I know, but
yeah. So they've been
it's
delaying.
the same launch, right?
Yeah, they've been delaying this launch for a bit, but the first launch they had was not a success because for some reason I forget why they had to basically abort the mission. Just as a refresher, the Rocket Lab rocket is called the Electron, and it uses the Rutherford engines,
Not the Proton,
not the Proton.
the
that's
Russian iteration that just
spins upside down and points downwards.
and then blows up.
Yep, usually
Well,
upward.
honestly, those are the most entertaining. Like, can we be real? Like,
Dude, that's
like-
why Falcon Heavy is going to be fun.
It's like
Oh, yeah.
watching it's like watching a slow motion pencil twist upside down
and then
just
burst into
Do you
flame.
watch that often?
God, I
Yeah,
love
I
those.
do.
No,
I
but
do that all the
so
time.
one of the reasons that Rocket Lab is special, besides the new tech that they're using, is there a medium? Are they a medium or lightweight lift?
Medium to light. They're light. They're light. They're very light, actually. They're like the smallest payload to orbit.
Yeah,
they are the lightest.
So the Rocket Lab is a lightweight rocket launch company, basically, and which means they have a much smaller rocket than the ones that like SpaceX and NASA launch. So they're going to be taking smaller satellites, which means that smaller companies don't have to pay at like the super expensive price for a Falcon 9 to get a very small satellite into orbit.
Yeah, so it's super light. Yeah, so the mass of an electron is about 9.109 times 10 to the negative 31 kilograms. That's quite light, and the Rocket Lab Electron is seeing pretty much the same type of weight, right, guys?
Dude, I heard that the Falcon Heavy lifts about that much currently.
Yeah, that's pretty light.
Yeah, that's pretty light. It's pretty.
How does that compare to the Saturn V?
Anyway, going back to
for those of you who didn't catch that, Adam's talking about an actual electron.
But actually, if you look at the Rocket Lab website, it's almost like reserving like spot in the theaters.
Oh,
to actually reserve payload.
Yeah,
it's
they have
like,
the book my launch button.
Yeah, exactly. you guys can go check it out. I think it's
process.
rocketlab.com.
We'll have it linked in the description.
We will.
So
but basically, it's just like a button that says book my launch, and you choose exactly where it sits in the payload bay, and
it
gives you like exactly how much it costs, instead of having to like actually interact with people and like do all that stuff that we don't like. But yeah, it's pretty neat, if I say so myself. No.
Yeah, yeet.
So Falcon Heavy, why don't we talk a little bit about that?
Yeah,
there's not really much. There's not much to talk about.
So as you guys
talking about
the last episode,
we were planning on viewing the Falcon Heavy launch
back in December,
the 29th of December, when it was originally slated to launch. The boys were gonna come down from up north. They're from up north. I'm from Florida. They were gonna come down, meet me, and we were gonna drive up to KSC, watch the launch.
What's
KSC is Kennedy Space Center, where lots and lots of launches happened. Cool place.
We were supposed to watch it, but no, it didn't happen.
So first of all, now the static fire, which is basically just testing the engines, which they have to do before launch. The static fire that used to be scheduled for like a few months ago, now
4 years ago.
Yeah, pretty much. Is now pushed back to this Monday, and which is tomorrow for the people who are listening to the podcast on the day of the release, which is going to be no one.
Honestly, if you're listening to this on Sunday, email us and we'll send you a T-shirt.
Dude, we will come over to your house and high five you.
Dude, we're gonna get 5 people on that. Like that's not a few. That's like a lot.
How are we gonna get 5 people?
No, 5 people are actually gonna watch.
Dude, I just won't post it until Monday.
Post it Sunday like 11:59.
We get 100 views.
100 emails.
Anyways, and
listens. I guess.
The Falcon Heavy launch has been pushed back to February. Woo! Who wants to wait?
Oh yeah. Dude, wait. It might
coincide.
It might coincide with my birthday.
So we'll go down to Florida for your birthday.
Might coincide with my birthday.
Yeah, why don't we
coincide with my birthday?
Let's drive. Let's drive.
You don't.
Honestly, it's probably gonna be on my birthday.
No.
Back in December again.
So Justin, tell us a little bit about the ULA launch.
So ULA, the United Launch Alliance, which is kind of like the conglomerate of Boeing and Lockheed Martin, they launched the 4th geosynchronous satellite in the U.S. Air Force's Space-Based Infrared Sensing Program, which is basically an array of satellites to sense missiles, so intercontinental ballistic missiles, which can have nuclear warheads on the top, such as what Russia has and what North Korea is attempting to manufacture. Keyword attempting, because they suck.
Yeah.
They actually don't.
Wait,
suck.
Wasn't there incoming missile threat that went off in Hawaii?
Yeah.
No, wait. Yeah, do you guys know what happened?
Yeah,
I don't.
It was a false alarm.
It was a drop-down menu, and he chose the wrong one on a drop-down menu.
Get out of here.
Yeah, that's how it was. It's test emergency systems and emergency systems.
Nice.
And he chose the wrong one.
Nice.
Anyway.
That's why you gotta make some very very good GUIs. Graphical user interfaces.
Mm-hmm.
Or else
GUIs are important.
Buoys are very important.
So this was the Atlas V411.
Dude, 5. Atlas 5.
This is the Atlas 5 411.
Dude, I love the Saturn V. You guys want to play some GTA V?
iPhone X. And it was like the perfect. It was a perfect rocket in ULA's lineup for this because of the lift capacity, and they were going to geostationary orbit on this one.
What's a geostationary orbit?
So, to go back to what an orbit is basically.
Circally around the Earth.
Yeah, circally
It's
around
when
the
you
Earth.
when you go up, but you don't have to come back down.
Yeah, but basically the.
But you don't go any more up either.
So you're going fast enough that you're falling away from the Earth at the same rate that you're falling to the Earth, or you're going away faster. Geostationary basically means the rotation of the Earth is equal to the angular rotation that the satellite experiences around
Or
Earth.
at velocity.
Yeah.
Angular velocity.
Yeah.
Oh, I said acceleration.
You said rotation.
So
Okay, let me re-say that. So Konstantinos, what geostationary orbit is when you launch a satellite to a distance above Earth that the angular velocity is equal to the angular velocity of the Earth.
No.
Yes, it is.
Anyway,
The rotation.
to explain that simply.
Oh,
it's
okay,
basically-
I guess technically it's rotation.
Oh,
Angular
yeah.
velocity of a point on Earth.
To explain that simply, it's basically when the orbit is just high enough where it takes exactly 1 day to complete the orbit. And 1 day is also, coincidentally, how long it takes for the Earth to spin around exactly once.
Oh, no way.
Yeah,
How long
dude.
is that?
Yeah, it's 1 day. So, let's talk about what we're working on this week. Justin, give me some of that.
Give me some of that.
So, everything I've worked on for the past month,
Which was?
a thrust structure for a low altitude demonstrator rocket, basically a thrust structure to transfer the force from the motor to the actual rocket.
Which means it's basically just...
No, it's not technical at all.
It's clamping the motor.
Okay, so I've been working on the connection between the motor and the rocket itself so that the motor can push the rocket.
Can you just super glue it in place?
You can't super glue it because the super glue will not be strong enough to hold the rocket like that. The shear strength of super glue is not... Okay,
Wait, are you sure?
The lap shear, yeah, I looked it up.
Oh, yeah?
I legitimately had to do calculations on all that.
Bet.
You want to see the spreadsheet?
No, bet we can't use super glue.
Dude, you probably cannot.
You can't.
Oh, yeah?
I did the
Oh, yeah?
calculations, dude.
Rocket epoxy, dude. Rocket epoxy solves everything.
It actually
super
doesn't
glue.
because... So,
Yes, it does.
no, it doesn't because...
Why? Then why is it called rocket epoxy?
Yeah, so anyway, I was working on the that interface, and I presented it, and I was told that we need to redo basically the entire thing. There was no fault on anyone's side. Like, it's not like we did anything wrong. It was the motor that were being supplied. The diagram of it was different than what we thought it would be. So, like, the shape of the motor was much different than what we thought. So we have to go in and redesign the whole thing. But in the end, I do think that it's going to be a much better final design. So we're going to, instead of having a dedicated fin can and thrust structure, we're going to integrate them so that it's a simpler to manufacture. And a fin can is like the fins on the rocket, how you attach them to the rocket. That's what a fin can is. And a thrust structure is how you transfer the the pushy force into the rocket.
The pushy force. You guys want to know something that's quite disappointing? So we've had the NASA program for about 60 years now, over 60 years.
Yeah, over.
And what's quite disappointing is that we've had multiple programs. All right, we've been to the moon, sent multiple satellites up into space, several launches, inspired private industry from launching rockets with NASA, and the most popular and widely known accidental technology derived from that is space ice cream.
No.
Yes, space ice cream.
Oh no, I'm thinking of the
Dude, no. What about winglets?
What
And,
about,
no, dude.
What about Velcro?
No.
What about Velcro?
No, why do kids go to this Kennedy Space Center? Right?
Dude, okay.
Space ice cream. Okay, that's all they care about. Like,
Adam,
they sell
Adam.
space ice cream
Wait, what-
at
what?
Ron John Surf Shop.
What is your source?
I've been to Ron John's surf shop.
Wait, what about like waterproof zippers?
No, dude.
Dude, what about
aluminum?
What about upside down pens?
It wasn't like mass produced until the
Upside down pens. Come on.
Upside
What
down?
about you wouldn't have a big ballpoint pen without it.
Damn, dude.
Dude, really?
Yes, but you wouldn't have space ice cream without. Like, come on.
Dude, I bet.
What about isogrids, dude? You wouldn't have gimbals either.
So Adam,
What was the main reason you went to the Kennedy Space Center when you were young?
was to look at rockets because I was freaking amazed by them.
It was not because
Dude, I didn't even know.
they told you about space ice cream in
I
school?
didn't know.
It was
space
'cause-
ice cream
it was
was a
'cause
thing.
about
I was
zippers.
from Greece. So Adam, what are you working on this week, or like since we last talked?
So since you guys last heard from me, I've been working on a reaction control system controller
Ooh,
and
do tell more.
doing some logistics and calculations and shopping, creating shopping lists for the vacuum stand that Konstantinos and I are
What's a
creating.
vacuum stand? Why do we need it?
So a vacuum stand, or this specific vacuum stand, the reason we're using it is, as we mentioned a little bit earlier in the year, in the first episode, we have participated in the cold gas thruster competition, which is basically creating like a nozzle, basically creating a fancy hole that creates more pushy force than other holes.
We're making a miniature rocket engine.
Yeah, like the bottom part that looks like a bell. We're designing that, over designing it. Anyways, so
Cut a leg off.
Oh yeah, Justin's in this competition too, but he's gonna get creamed.
That's not even true, dude.
that is kind of.
You guys don't even have an isogrid on your base plate.
Dude, bet we don't. But
Yeah.
we have way better technology.
I actually was thinking about doing an
Technology.
adjustable throat for it.
Dude, don't.
And
Anyways, going back to what we're working
Yeah,
on,
yeah, yeah.
it's a vacuum stand. So basically, we want to test these thrusters in very low pressure, similar to like say very high in the air,
Outer
or
space.
in closer to space, to see what kind of pushy force we can get. So
Technically, the atmosphere goes on forever, but whatever.
So to do that, to simulate that very low pressure environment, we're basically taking a very big box and taking all the air out and basically turning on the thruster in that big box. But that takes a lot of engineering to figure out how fast the box fills when the thruster's on and how strong the box needs to be and how big the box needs to be. That's essentially what we've been working on.
Did you mention that the physical characteristics of a nozzle change depending on the atmosphere that you're in?
I did not.
There you go.
So basically, that means that depending. So when you have a nozzle,
should we
you
explain?
have So when you have a nozzle, you have a choke point, which is the smallest point of the nozzle. It's also called the throat. And then after the throat, you basically kind of expand out. Like if you were to look at what's kind of like a bell nozzle looking, or what's kind of like a nozzle, bell nozzle.
Oh, I got this.
Exhaust, but no.
Hang on. Give me a sec.
Umbrella? No.
It's like those cones dogs wear when they can't scratch themselves. It basically is very small around the throat of the dog in this case, but and then it expands out. And what that does, it basically causes the gases moving through the nozzle to go very fast, which is good. When you are operating at different pressures, so right now, like when we're close to sea level, the pressure is around 15 psi.
What's a PSI?
PSI is pounds per square inch. It's
Same thing that you put in your tires.
it is it is a way to measure force on an area on some surface.
Dude, it's like it's force over area.
Dude, it is like pounds per like square inch
Dude.
or something.
What's Young's logic?
Dude. So when you have a thruster operating at sea level at 15 psi versus when you have it operating at a higher level, say at 10 psi, they're going to have very different designs because there's different pressure basically pushing on the outside of the thruster. And that's why we're trying to basically simulate that by having a box with less air in it. Which is kind of similar to what you'd see done in industry. You first try to model it, or do your best to model it like computationally. Like you make a program that's depicts this box, and then you build this box, and try to get some valuable data.
Yeah, you know that redneck engineering, when you see like rednecks put together some random contraptions, that's what we not do. So that's what we try and avoid.
Basically, what we're doing is testing we have to redesign the cold gas thruster for a different scenario to test our engineering abilities.
Pretty much, yeah.
Okay.
And it's a competition. So Justin and his partner Felix are gonna get like completely blasted.
They're just gonna.
That's just not true, dude. Oh.
Do tell us more.
Okay.
Doesn't say anything.
So, if you back to the SpaceX launch in Vandenberg when they were launching right at sunset, when it's very high up, you can see a really big plume of gas.
Ooh, what?
That's because
aliens.
That's because one, aliens,
and two, chemtrails. So the reason it expands out like that is basically, as we said, when you're up higher, there's less pressure from the outside, and
so
there's the same pressure coming from the gases exiting the
higher
engine.
Actually.
Yeah, no, it's the same as when it was before. Yeah. So it's basically like.
Wait, do they? Because after they throttle down, then they throttle all the way back up.
Yeah, it depends. Not always. Sometimes they do it for like max Q and stuff. But obviously, I'm gonna cut that out.
No, keep it in.
So
we should just read RPA during this. Okay,
so basically, there's more. The gas from the engine is pushing with more force than the gas from the air on the outside, so it kind of is just able to expand.
Yeah, so are you guys familiar with the
reason,
Bernoulli effect? Oh my.
Okay, so you know when you fly on an airplane, when you have like a bottle of water or a bag of chips, then you fly and you're at a really high altitude, then the bag of chips expands and like your thing of water, when you undo the cap, there's like a psst, the hiss sound because gas is released.
Because it's mad at you.
Because the gas being released from the water bottle.
It wants you away from its kids.
The gas being released from the water bottle is the same concept as the engine at a higher altitude.
Yeah.
No.
Okay, so now that we covered that, well, how do we get? Oh, we were talking. Oh, that's why Adam and Konstantinos are building a vacuum chamber so we can try and do that.
Well said.
Well, so we could do that, yeah.
Okay, what are you guys working on? Anything else?
Well, the control system.
We did the control
cool.
system. So.
But that's also too complicated to explain. So basically, another thing we're working on is
steering.
So basically, another part, as Adam mentioned earlier, that we're working on is the RCS control system.
Reaction control system?
No. Yeah. Well, yeah, actually. The control system for the control system.
That actually is true.
Technically.
Yeah, so RCS stands for Reaction Control System.
So that's just a fancy way of saying. That's just a fancy way of explaining steering a rocket. So all that does is basically, it controls how much you can rotate the rocket. And there's a lot of complicated math that we're not going to go into. But basically,
it boils down to the fact that we want to make sure a rocket stays on course.
Yeah, and we don't want it to start spinning around really fast. So basically, we blow gas in the opposite direction. So as we said earlier, there's thrust, or also known as pushy force, in the direction opposite of rotation.
Yeah, I have the perfect example. You guys are Wall-E. I was gonna say that, Wall-E. So you guys know in Wall-E when it was a fire extinguisher?
Yes.
Yeah. So you had
right?
Yep.
So like Wall-E.
Wall-E and fire extinguisher.
Yeah.
Yeah, he had a fire extinguisher and he was like floating through space.
Yeah,
so,
yeah. Exactly.
That's real.
Yeah, so because
that's like actually.
That's like
that
actually happened.
Yeah, that is actually like exactly how rockets work. It's
same concept.
Because you're basically pushing gas out the back really fast, which causes basically
same way airplanes work too.
It's basically how anything ever that creates thrust works.
Yeah, if you fart on Pluto, will you
You
fly.
won't.
Dude, I want to see what the displacement would be from a fart. What's your acceleration based on a fart?
Yeah, that'd be interesting.
Dude, you can figure it out. You
What
can
if you
figure out
put a- what
rotation
if you
and
put a-
everything. Anyways, so let's go back to actually talking about rocket science.
Going back to ULA, they used they have solid rocket boosters, which is like a second rocket.
We did that last time.
Well, this is the same thing on this one.
What? Yeah, but we already.
I wanted to say that they ignite 3 seconds after the main rocket. Quick random fact about the ULA launch. The solid rocket boosters, which are on the outside of the rocket, we talked about them in our last podcast. They ignite at T-minus 0 seconds, while the center liquid rocket ignites at T-minus 3 seconds.
Generally, just about, yeah. So, how about we talk a little bit about, like, at a very basic level, what some different rocket engines are, types of rocket engines are.
Okay.
So, Adam,
What's your favorite rocket engine?
Want to start us off with solids, Adam, since you have that high school experience, all that. Adam, what is a solid rocket booster?
Okay.
Or solid rocket engine, or motor, or solid rocket.
Okay, so
hang on.
yeah, there are in rocketry there are different types of fuels, right? But the two main ones are liquid propellant and solid propellant.
And then hybrid is also somewhat.
So in rocketry, the entire goal is to have thrust, the pushy force on an object, and there's a bunch of different ways you can do that. There are a bunch of different ways to do that efficiently. Depending on different scenarios, there are a bunch of traditional methods which we're just about to cover, but please know these are not the only ways that thrust is created. There are less traditional ways, such as ion drives, that are used in industry, but are very niche and really in the weeds, so they're not too applicable to any launches you'll see ever, actually, and they're only used in deep space. So with that, Adam, take it away.
Yeah, so
Adam, what are solid rocket motors?
Yeah, okay. So solid rocket motors imply what they say, right?
They pretty much.
Yeah, they the fuel is composed of solid grain fuel.
So
yeah, their fuel is composed of solid grain fuel. Two main components: the oxidizer and the fuel itself. And the oxidizer aids in the combustion process. So, lighting it on fire.
Gasoline and air intake on your car.
Yeah.
Yeah, so it's kind of like if you're to have the gas and the air in the car, only they're in a solid form. So, the main type of rocket engine that's used to get to space is liquid engines. And as the name implies, they use liquid fuel and oxidizers. So the liquid fuel is just like gasoline that you use in cars. It's actually very similar oftentimes. Like for Falcon 9, which is SpaceX's launch vehicle, they use basically a refined version of kerosene. That's called RP1. It stands for Rocket Propellant 1. And then the oxidizer is also liquid. And they cool it down a lot so it gets very dense, basically. And then they pump it through the engines and ignite it.
So normally in combustion, you're going to have the source of fuel. Say for a campfire, your source of fuel is wood. And then you have an oxidizing agent, which is in normal life just the air around us. But when you're in the vacuum of space, there is no air, so you have to bring your own oxygen.
You gotta bring your own air. You gotta bring like a big bag of air.
Bring back a big...
A notable difference between solid and liquid fuel is that solid fuel comes... the oxidizer and fuel come already mixed, as opposed to the liquid propellant, which you typically you always like house them in separate containers, separate tanks.
Yes.
And you mix them while
So when you're bringing your oxygen with you along with the fuel. So it'd be taking a big bag of air and a bunch of wood into space and then lighting a fire.
Pretty much.
And we keep them separate because if they were together, what would happen if they were together?
If they were together, it would be... Well,
it depends on which
No,
fuel.
it's because you have to mix them at a ratio to at a proper
it's-
ratio.
So then
ratio
why don't
to
they have one tank?
Because
then also
then
I
you
think
can't
they're
mix it at
kind
a
of
proper ratio.
different temperatures also, and like You don't have... Oh, so the main reason actually they don't do it together is because when you're going through the pipes, there can be heat spikes, and you don't want them to ignite.
Really? That's the only reason?
Well, that's not the... Wow. That's not the only reason.
I mean, if it's a hyperbolic, it's different.
Hypergolic.
Hypergolic. Damn, it always
Hyperbolic.
Hyperbolic.
Yeah, that's right.
But that one of the main reasons is so that they don't ignite, because that would literally just explode everything, and that's very possible. But yeah. So they're generally kept separate so they don't accidentally go off. But yeah.
So now,
Justin, tell us a bit about maybe something in between liquid and solid.
So in between liquid and solid, there is hybrid, which is a combination of liquid and solid.
Kind of like hybrid cars. They're a combination of gas and electric.
So you have the in a hybrid system, you have the component of the solid rocket fuel that you get from a solid rocket motor, and you have the component of the liquid oxidizer that you get from a liquid fed system. And this is a melding of the two. What will happen is you're going to have holes going through the rocket motor in the direction of like the tube of the rocket, and you're going to run oxidizer through that. So then on the walls of those holes, the oxidizer is going to mix with the fuel, allowing for combustion. And there are a bunch of different ways to do this, or a bunch of different materials to use. An interesting fact that I recently learned about is a lot of solid rockets are made from car tires, or a similar material to car tires.
Yeah.
So you are literally driving around in your car on rocket fuel. It's absolutely amazing to me. Another common one that amateurs will use to make rocket engines is plexiglass.
Mm-hmm.
Or not plexiglass,
acrylic.
Acrylic, yeah. So acrylic, which is where's acrylic used nominally?
It's a type of plastic that's clear. It's kind of used in applications where
acrylic windows, acrylic.
Yeah, like acrylic windows, where you want to be able to see through something, but you don't want glass to shatter.
Speaking of niche fuels,
and hang on, wait. The reason that these materials work is because they're all petroleum based. They're all made from byproducts of oil. So tires are generally made from petroleum, a petroleum-based thing, and same thing with acrylics and normal plastics.
And that means they have a lot of energy.
So yeah, the key is you want a lot of energy in a really small space, and just like gasoline does, that's like that. Think about the difference between wood and gasoline. If you have a block of wood and a cup of gasoline, the cup of gasoline is going to have a much bigger fire than the block of wood.
So Adam, tell us a little bit about the pros and cons of using solid rocket fuel. Very like basic level.
Okay, yeah. So typically with solid rocket fuel, you get. Oh, it's just easier to handle. It's much easier to handle, maintain, and store than liquid fuel. That's the primary benefit of
also it's like
rocket fuel.
it's more reliable. It's more liable to for ignition.
Oh, it's also provides much easier ignition compared to liquid propellant. You have to mix the liquid propellant, whereas solids you just lighting it. And speaking of, Justin was talking about niche fuels earlier. I would like to bring up rocket candy.
Yes.
Yeah, it's quite an interesting fuel.
Dude, I love that rocket. It tastes so good.
Don't eat rocket candy.
Do not eat rocket candy. Yeah. So
don't eat the yellow snow.
Anyway, rocket candy.
For those of us who are from Florida.
Rocket candy is a type of solid fuel in which the fuel is made of sucrose or glucose or even fructose.
Sugar.
Yeah, sugar, basically. So you typically mix these fuel components with an oxidizer such as potassium nitrate and perhaps a few different additives to make combustion easier. And you can actually create rockets with this fuel.
Yeah. So, what are some of the cons about using rocket fuel?
Boom.
The cons of using rocket fuel, that's quite broad.
Sorry, cons of using solid rocket fuel.
So yeah.
Dude, why are rockets bad, dude? Like, ethically.
So yeah,
No, like that you can't stop it.
like
and you can't.
I'm trying to how do I explain it easier?
once it's on, you can't turn it off.
Okay. So yeah, one of the cons of solid rocket fuel is that once it's ignited, it cannot stop.
You can't put the fire out.
You can't put the fire out. Whereas with liquid propellants, you can throttle them on or off.
Because you can adjust how much gas goes into the chamber.
Yeah.
Pretty much.
Gas as in like the analogy to a car, not it's actually a liquid.
You can also achieve better specific impulses with liquid propellants.
Better efficiency.
For the layman, specific impulse is pretty much just how fast your gases are coming out of the bottom of the rocket.
Yeah, exactly, which contributes to the efficiency of the rocket.
Yeah. And thrust, on the other hand, is that same velocity multiplied by the mass of the same propellants coming out of the end.
So some of the disadvantages of using liquid engines or liquid systems are that they're generally more complex because they need more parts, like the pump, and you have to transfer them from the container to the engine. And also you have to store them somewhere before the launch, which is oftentimes dangerous, and generally they're more expensive. But they do have their benefits. Then hybrids, which are somewhere in between, have a little bit of everything. They, unlike solids, can be turned on and off, but also, unlike liquids, they are less efficient. They're somewhere in between, which makes them a little bit less optimal for use used by aerospace companies. That's why you don't really see them often.
Guys! We missed the Rocket Lab launch. We're gonna rewatch, or we're gonna watch the Rocket Lab launch that we just missed, and then we'll get back to you guys. We're back, guys. So we just watched. We just watched. We just watched the Electron launch that we missed. What time did it launch? Around 8:30.
Around 8:30, yeah.
So after
all these delays, Rocket Lab finally got to launch their Electron rocket, and it went very well. They achieved orbit about 20-something minutes ago, which is awesome to see. They're the first company to. They're the smallest. I'm pretty sure they're the smallest. Definitely the smallest private rocket to orbit. And they're also the first to test electric pumps, which is more efficient. It's kind of like
fiber, no?
They also have a very much carbon fiber body, like mostly made of carbon fiber.
Wait, no, are the Rutherfords carbon fiber?
No, they're 3D printed. So, Adam, what was the payload that the Electron got into orbit?
Yeah, so Rocket Lab's goal today was to send 3 experimental payload satellites into orbit, and they did exactly that successfully.
They did indeed.
It was very nice. Blue skies with a couple clouds.
Yeah, it's a beautiful launch pad on New Zealand.
With open rolling hills around the launch pad with a backdrop of a crystal clear ocean. Just as the rocket passed through the clouds, the gases expelled by the engine began to condense, leaving a beautiful white trail following the rocket up to space and towards a more accessible future of rocketry. Thank you very much for watching. I'm Justin Fischetti.
I'm Adam Kotler.
And I'm Konstantinos Durantis. See you next week. Don't forget to dampen your control systems.